Hello everyone, this is the part 4 in our video playlist, and in this video we're gonna write a code to solve the time varying temperature profile of the bar in part 2 using an implicit differencing, which is also known as Crank-Nicolson method. Vary the time step to empirically show that there is no apparent stability limits on the choice of dt. Okay, so previously we solved the same problem with explicit differencing method, and we found that the higher limit for our dt cannot exceed 0.5. So now we're going to use the implicit differencing method to show that there are no limits. So there are not going to be limits and our graph is going to be stable. So before we jump to the Python, let's do some work on our notes so that we can apply our equations to the Python immediately. Okay, so previously we derived that the equation that the first derivative of the temperature respect to time is equal to the thermal diffusivity times the second derivative of a temperature respect to x, right? And okay, so we know that the temperature of first derivative of a temperature can be also expressed as the temperature at J at a later time minus the temperature at J at a current time over delta T, right? That's going to be equal to the alpha times. So previously when we did the explicit differencing method, we just took the second derivative of it. So we just found how the slope is changing. But this time, we're going to do the same thing, but we're going to take the average of two different slopes, okay? So my equation then is going to be the temperature at J plus 1 at times equal to N minus temperature 2 times temperature at J at times equal to N plus temperature at J minus 1 at times equal to N over delta x squared. So that's the second derivative at a time N. So minus, so we're going to do the same thing but for the time N plus 1, okay? So the temperature at J plus 1 at time N plus 1 minus 2 temperature at J plus 1, J at times equal to N plus 1 plus temperature at J minus 1 at times equal to N plus 1 over delta x squared. And to take the average, we need to divide everything by 2, so we're going to apply 2 right. Okay? So if we want to manipulate our equation, we can say that we can multiply the delta t to this side and we can get the delta x squared out of the parentheses. So what I'm going to have is temperature at a later time minus the temperature at a current time, temperature at J is going to be equal to the alpha times the delta T over 2 times delta x squared. And what I'm going to have inside is Tj plus 1 and minus 2 Tj and plus Tj minus 1 and minus Tj plus 1 at a later time plus 2 Tj at a later time, so negative becomes positive, right? Minus Tj minus 1 at a later time. Okay, so now what we're going to do is we're going to express this thing as u. So previously, in our second part, we expressed the constant as r, right? But this is a bit different from that constant because we have a factor of 2. So it is the same thing as divided by 2. So So we're gonna call it u, and then what we're gonna do is we're gonna have an equation with the t's at a later time in one side and with the temperatures at a current time in one side. Okay, so I'm gonna have Tj at a later time. That is gonna be okay, so how's that gonna be? I'm gonna have negative u Tj at time is Tj plus 1 at time is equal to n plus 1 plus 1 minus 1 plus 2u times the Tj at n plus 1 and also minus u Tj minus 1 at n plus 1. And for the right hand side, I'm gonna have everything, all the temperatures, but at a current time. So I'm gonna have u Tj plus 1 at n plus 1 over 1 minus 2u Tj at n and plus u Tj minus 1 at a current time. Okay, so in our earlier part, previously when we did it with explicit differencing method, we had only one temperature that was connected to the time to a later time, but here we have three temperatures, right? So we cannot use a linear model anymore, but what we can do is we can try to use the matrices to solve our problem. So if we imagine our bar, so we know that the temperature at two ends are going to be the different, right? And we have everything is divided into dx's. So this is going to be the J0, 1, 2, 3, 4, 5 up to n, right? And this temperature is going to be n minus 1. And we know the temperatures at a left side and a right hand side. Okay, so what we're going to do now is we want to find these ones, right? So because the left temperature on the left and the temperature on the right side of our bar is going to stay the same, so we're going to create a array so we're going to create a matrices for our temperatures at a later time. So I don't have to include all the temperatures at times equal to n. Temperature at times equal to n. And that should be divided with the u. So the whole side now I'm expressing is the left hand side of our equation. And here I'm going to have a matrix that is equal to the right hand side of our equation, okay? So when j is equal to 1, so we're trying to find the j's from 1 to n minus 1, right? So when the j is equal to 1, I'm going to have Tj plus 1, so temperature 2. So kind of it is multiplied by temperature to the 1, right? So when I plug in 1, okay, let's start with j is equal to 2 because it's easier to explain in that way. So when I say j is equal to 2, we're considering when the temperature, we're considering the T3, T2, and T3, T2, and T is equal to 1. And when the j is equal to 0, j is equal to 1, we're considering T2, temperature at J is equal to 2, temperature at 1, and temperature at 0. Okay, and we know the coefficients for that, right? Okay, so here it's gonna be, so in order to find T2, like the coefficient of a T1 is gonna be negative U, and the coefficient of a T2 is gonna be this 1 plus 2U, and the coefficient of a T3 is gonna become negative 3 when negative U when J is equal to 2. Okay, so at a later J, so when J is equal to 3, that's going to be the same, but we're moving one step to the right. So it's going to be 0, negative U, 1 plus 2U, and negative U. And a later J, it's going to be 0, 0, negative U, 1 plus 2U, minus U. Okay, so the trend is going to continue. So, and we know, and now here we can notice the continuity in our, as a diagonal, right? So we're going to need that information to use it in our code, okay? So on the right hand side, I'm going to have, so when the J is equal to 1, I'm going to have U times T2 plus 1 minus 2U, 1 minus 2U, T is equal to 1 plus U times T is equal to 0, right? But we also have this temperature right here, so I'm going to have 2 times T, 2 times U, T is equal to 0, okay? And for the next, I'm going to have U times T3 plus 1 minus 2U T2 plus, this time U is equal to T1. Okay, and when J is equal to N minus 1, I'm going to have 2 Tn's because we're also considering this, the right hand side, right? So it's 2 times U Tn plus 1 minus 2U T N minus 1 plus U times T N minus 2. Okay, so now what we're going to do is we're going to use solve. So these temperatures are for the time is equal to N plus 1 delta T, right? So these are the temperatures at a later time. So we want to solve for them. So we're going to use SciPy optimized linear algebra equation to solve for this unknowns using our Python code. Okay, now let's try to apply our equation we found, like the matrices, Crank-Nicolson method, to our Python. So we're going to use the same file we used for our part 2 to solve it with explicit differentiating method, but this time we're working with matrices, right? And so in order to work with matrices, we need to import a library from SciPy linear algebra. We're going to import solve bandit. So solve bandit is a function that uses a matrices, like the diagonal matrices, to find the value. So using the solve bandit, we know this matrix, this array and this array, so we can solve for the temperatures at a later time. Okay, so what we are given, so we're given that N is equal to 20 again, right? And we're given that the temperature so we're given the temperature to the left. Okay, let's say temperature 0, temperature on the left, and temperature on the right. So we're given those values, right? Right. Okay, so let's say, like, let's change the temperature now, like make it 25, and for the T left it was 50, right? and T right is going to be 80. And we also know the alpha dx and dt. So our alpha was 1, our dx was 1. Okay, let's make our dt 0.5 first. We're gonna check if it is valid for other values after we plot our graph, okay? And we know that our u is gonna be equal to alpha times dt over 2 times dx squared, right? Okay, I'm gonna run it. Okay, so now we're trying to find, we need to import, to include our matrices. So we're gonna start with, what we can start with. Okay, let's start with the negative u's right here. Okay, how I'm gonna do that is, so let's start by creating an array for our temperature. So that's gonna be numpy of like zeros. So it's gonna be the array that is gonna consist of, no, we already have an array for temperature, right? So let's have a value for our diagonal matrices. So I'm gonna call it a bands. Okay, so I have 3 values in our diagonal that are kind of repeating, right? So I'm gonna have negative u, 1 plus 2u, and negative u again. So which means I need to use 3 rows, and the number of variables I'm gonna have is gonna be n minus 2, because we're not considering the left side and the right hand side of our bar. So a band, so so the first row of my bands gonna be negative u, right? So it should be negative u, but I need to include like which specific values. So that's gonna start from 1 and continue until the end. So that's gonna be my values for negative u. And a band, my second row, that's gonna be u, like 1 plus 2u, right? So it's gonna include all the values, because it's in the center. It's gonna start from t1. It's gonna start from t1 and go until the end. So, and then that's gonna be 1 plus 2u, right? Oops. 2 times u. Okay, and another row. So the third row, so because of the numpy, like the Python indexing starts from 0, 2 is going to be our third row. That's going to be the negative u this way. So, so it's going to be the number starting from 0 till the negative 1. Negative u. Okay, now I have all my bands, like the matrices in here. So now I need a plot. So I'm gonna get this thing. Okay. So I'm gonna change this row only. Okay. So I need to include this matrices to my Python, right? So I'm gonna call it B. And that's so, and that's gonna be equal to the U times the temperature at 2. So I can represent that as like temperature at J is equal to, that's going to be like starting from 2 till the end, right? Okay, plus 1 plus 2 times U, the temperature 1. So that's going to be, okay, I forgot to use the T here because I'm getting that from the temperature array, right? Times the temperature. So like for temperature 1, that's going to be numbers from 1 to -1, right? And for the temperature, and then plus U times the temperature, starting like up to -1. Oh no, -2. Okay, and then my temperature value, so it needs to be updated every time, right? So now I'm going to use the solve bandit function. So for our solve bandit, we need to give the variables. So it is solve bandit is using kind of so it's going to use the guesses and the function, I like the array abans. And the equation that we need to get for the right hand side. Okay, before moving on, let's try to check it, okay? Just to make sure it's working. Okay, if I'm gonna run it, okay, it's showing an error message here. So I just realized my error. So when we were doing the first part, we wrote it incorrectly as T0, but we had to TI because then later I created a temperature array with n number of temperatures and all of them are TI. And also the first value of my temperature is going to be the T left, which is going to be the temperature on the left side, and the last one is going to be on the temperature on the right side. If I run it now, it should be fine. And here I should include this thing here. So because of the fact that I have another B0 at the beginning and another like T0 at the beginning and another Tn at the end, I have to include them, right? So it's going to be the temperature 0. And my B, the last value is going to be equal to B, the last value, plus, so it's going to keep updating our values. T of the -1. Okay, now let's try to plot it. Okay, here we go. So our plot works, but we're testing it with dt is equal to 0.5, right? With the explicit differencing method, it is still within the bounds. So let's try to change it to 0.6 to see if it's going to be stable. Here we go. So it is working, right? It's not causing any problems, or it's not going to infinity. Where in our implicit differencing, when we did with explicit differencing method, when we increase it to, let's say, like 505, even the minor change would cause this kind of problems, where in Crank-Nicolson method, no matter how much we change our dt value, it's still going to be stable. So in the next part of the video, we're going to theoretically prove with the one Neumann stability analysis that dt can take any values so that our graph to be stable. Thanks for your attention.